Another thing that we might want to do is interpret coefficients. So I have my kind of recipe sentence here. For a 1 unit increase in x sub I, we would expect a b sub I unit increase or decrease in y, holding all else constant. So I'll write this out for the average temperature. For a 1 degree increase in temperature, we would expect and now I need to flip back and look at that b sub I. And that coefficient was the 5.5. A 5.5 person increase in the volume on the rail trail. And all else constant, that's kind of the lazy way to do it, where you're just kind of throwing everything in. If you only have a few variables, I think it's better to say holding and then putting in the name or names of the other variables. So in this case, holding cloud cover constant. And so what that means is we're saying, we're gonna say, if you had 2 days that were the same amount of cloudiness, for a 1 degree increase in temperature, we would expect to see 5.5 people more on the warmer day than the cooler one with the same cloud cover. And I could do the same kind of thing for the cloud cover coefficient. For a 1, and again it's an octa, 1 octa increase in cloud cover, we would expect and again, I need to flip back and look at the coefficient. It was negative 17.42. So what I'm going to say is we would expect a 17.42 person decrease in the volume on the rail trail, holding average temperature constant. So one thing to note here, because I had a negative coefficient, I said it's going to be a 17.42 person decrease in the volume versus a 5.5 person increase in the volume. For a positive coefficient, you say increase. For a negative one, you say decrease. And then for this one, what we're saying is if you had the same temperature day, so 2 different 60-degree days, one that has more cloud cover, we'd expect to see fewer people on the rail trail. And that kind of makes sense too. If it's a cloudy day, there's probably going to be less people out biking, even if the temperature is the same. So those are the coefficient interpretations. Another thing that we might want to do is see if the predictors are significant. And so we have the same kinds of hypotheses as we did for simple linear regression, but now instead of just beta 1, we're going to do tests on all the beta sub i's. But we're going to find the same kind of t-value where we find our fitted coefficient bi over the standard error, and then that is a t-value where we find the p-value in a t-distribution with the degrees of freedom equal to n minus k minus 1. So we're going to go look in a t-distribution, and we're going to look in the tails and see where that t-value falls. And then we're going to look at that p-value. So now I'm going to show you an even bigger model. This is a model that has 1, 2, 3, 4, 5 different predictors in it. It still has the intercept, and it's got average temperature and cloud cover, but now I've also put in precipitation, whether or not it's fall, and then whether it's a weekday. And this is the kind of output that you get from a computer. You get the estimate and the standard error, then it gives you the t-statistic, and it gives you the p-value. If we wanted to, we could reproduce this. So if we wanted to find the t-value for cloud cover, that would be the B1 value, negative 12.85, divided by the standard error, 3.473, or negative 3.69 repeating. And that's the same thing that was in the table, but maybe we want to confirm for ourselves. And then if we wanted to find that p-value, we'd need to go look in a t-distribution with n minus k minus 1 degrees of freedom. Now, I'm not sure I told you what n was in this case, but it is 90. And then k is going to be the number of predictors. Again, that was 1, 2, 3, 4, 5. And minus 1. The minus 1 is for the intercept. So it's basically the number of predictors, including the intercept, but we always set it up as n minus k minus 1. So in this case, 90 minus 5 minus 1 is 84. And so we'd need to look at a t-distribution with 84 degrees of freedom. Let's do that in StatKey. So here I am on StatKey. I'd click on the t-distribution and I'd put in my 84 degrees of freedom. So then I click the two-tail button, and then I'm going to change the negative 1.988 to be my test statistic, which was negative 3.699 repeating. Okay. And then it gives me my p-value. So I'm going to take a screenshot of that to throw into my notes. And what that says is that there's 0.00019 on both sides. And so if I added those two things together, I would get 0.0038, and that's the same p-value that we saw in the computer output. So that's where those p-values come from. And then there's a couple of questions here, like which variable is the most significant? And which variable is the least significant? We could ask, is fall a significant predictor? And I think I will talk about the first one, and then I'll leave the other two for us to talk about during synchronous class. So for the first one, which variable is the most significant, I would look at these p-values and I would look for the smallest p-value. And it's actually this one for average temperature. This is 2.6 E minus 0.6. That's like 2.6 times 10 to the minus 6th, or 0.000002. It's a very small p-value, almost 0. So the most significant predictor is average temp, and then we'll talk about the other ones during synchronous class. So I could look at my 2-predictor model, where I was just looking at average temp and cloud cover, and my 5-predictor model, where I have average temp, cloud cover, precipitation fall, and weekday true. Things are going to be different every time I add additional predictors. So the estimate, the slope for average temperature, does not stay the same. The slope for cloud cover does not stay the same. The p-values do not stay the same. So every time you add more variables into a model, the whole model changes. And the p-values are only going to tell you about how good a predictor is in the context of all the other predictors in the model. So when we did this 2-predictor model, cloud cover was very, very significant. It was almost as significant as average temperature. It was 1.6 times 10 to the negative 6th. But then when we added in a bunch more variables, that p-value, it's still significant, but it became less significant. That p-value got larger. And so every time you change the model, you're going to change all the estimates, all the standard errors, the statistics, and all the p-values. The other thing to know about comparing models of different sizes is that we might want to use R squared to assess a model. So remember, R squared tells us what percent of the variability in the response is explained by the model. So for my 2-predictor model, the model using average temperature and cloud cover explains 37.31% of the variability in volume. Compared to, for my 5 predictor model, the model using average temp, cloud cover, fall, precipitation, weekday, I think that's all 5, so and weekday, explains 45.82% of the variability in volume. So if we just look at that r squared value, which is given to us at the bottom of the model output, I've just pulled it off here so we can see it more easily. If we just look at that number, it looks like my 5 predictor model is much better. A lot more of the variability is explained with this 5 predictor model than with the 2 predictor model. But adding more variables is always going to increase the r squared, even if it's just random noise. And larger models are harder to explain to other people. If you just have 1 or 2 predictors, it's pretty easy to explain the model to someone else. If you have 5 predictors, it gets harder. If we are going to compare between 2 models, we probably want to use something called adjusted r squared. I'm not going to go into how that is computed. If you want to know that, take Stat 320. But adjusted r squared is more fair about comparing between 2 models. It doesn't always go up when you add more variables, so it will tell you if a model is better than another, even if they're different sizes. And so I've also put the adjusted r squared here, and it looks like even once we've adjusted, the adjusted r squared is still bigger than the adjusted r squared for my 2 predictor model, so maybe my 5 predictor model is actually better. But as the analyst, we should always be thinking about the context and whether we care about that little additional amount of variability being explained. Another way how to see how good a model is overall is if you can create one p-value for the entire model. And we call this process ANOVA. So we're analyzing the variance, like are we explaining significantly more variance? It's not quite the same as the ANOVA that we did when we were just comparing a lot of means, but it's got similar components. So again, it's one of those places where statisticians shouldn't name things. They've really overloaded the term. But the table looks pretty similar. So you end up with a row for the regression, a row for the residuals, and a row for the total. You get a degrees of freedom column, and you have the degrees of freedom for your model, which is the number of predictors. You have the degrees of freedom for your residuals, and you have the total degrees of freedom. You get sums of squares, you get mean squares. Your F statistic is also computed by dividing one of those mean squares by the other, and the p-value is found by looking in an F distribution. So this p-value will tell you if your model is significantly better than just using the mean, which it almost always is. So this one is 1.5 times 10 to the negative 9th, very small p-value. It's better than using the mean. And we could do the same thing with our 5 predictor model. Our degrees of freedom are a little bit different, but again, we get a statistic for the overall model and a p-value, and it looks like this model is also better than the mean. So just like a little bit of summary, multiple regression is much like simple linear regression, but it has more predictors. We do the coefficient interpretation in a similar way, but we add holding blah constant or holding all else constant. We do our hypothesis tests in a similar way, but our degrees of freedom are now n minus k minus 1. We can still use r squared to show how much variability is explained using the model, but if we want to compare between 2 models, the adjusted r squared is better. And we also have a version of ANOVA that can tell you if your overall model is better than the mean.